So hi everybody, so thanks for being here. So my name is Luc Robichaud, and my work was done under the supervision of Professor Jacob Krisch and funded by TDIN. So my work was done on the determination of optimal indium concentration and dot size for indium gallium nitride, gallium nitride on dot example. So it's a long title. We'll be going through it piece by piece, but I'm going to start off by telling you what are intermediate band solar cells and how quantum dots contemplate realizing these devices. So in traditional semiconductors where you have a valence band and a conduction band, any photon that has the energy of the band gap can be absorbed and contribute current. So you get access to a certain region of the solar spectrum here. Now in the case of intermediate band solar cells, you have what's called an intermediate band, and it's essentially a set of levels that is within the band gap. What this allows is the absorption of photons that were previously wasted, not being used. And suddenly, you have this increase of current that comes from absorbing these photons. Now, the second important aspect of intermediate band solar cells is that you can maintain a high voltage. The voltage is still given by the full band gap of the material. So you can maintain a high voltage by having a big band gap and increase current penalty. You can get more power out of it. That's the main driving idea behind intermediate band solar cells. Now, the efficiency of these devices largely depends on where the intermediate band is within the band gap. So, one way to figure out where to put it is to use boundary calculations. Now, the main assumptions made here is that there is no non-radiated combination and there is no current being extracted from the intermediate band. Now, what we actually calculate is the difference in flux, photon flux, going in and out of the device. Because any difference in the flux is caused by photons being absorbed by electrons who are then promoted to the conduction band and being extracted as current before being able to be emitted. So any difference in the fluxes gives you your current. So this type of calculation is done for a given voltage and band gap, so you can then on calculate power and efficiency. And in my case, I'm interested in gallium nitride, so my band gap is 3.4 dB. So here's a plot of the efficiency of the device as a function of where the intermediate band is within the band gap. So you're going from around valence to around conduction. And what you notice is, well, your maximum efficiency that you can get from these devices, from this material, is about 49%. And this was done under full concentration. Now, if we look at where the maximums occur, we see that the first one is about a third of the way from the valence to conduction, and the second one is about a third of the way from the conduction to valence. Both cause the same kinds of transitions within the device. And in peculiar, it's the second one that is of main interest to me for my work that's going to go on. So the second one happens around at 1.9 dB from the valence band. So that number will pop in later on. So how do we actually realize these devices in band systems? Well, one way to do so is through quantum dots. And what I've sketched here is basically the valence band and conduction band edge energies as you move from your host material, gallium nitride, to your quantum dot, and again into your gallium nitride. So here we're only considering one quantum dot. And what we notice from this sketch is that introducing indium into gallium nitride offsets the band towards the center, symmetrically towards each other. And so you end up with these sort of quantum wells here that end up containing discrete energy levels. And it's through transitions between these levels that we're able to match this system to that of the intermediate band. So for example, here we have the full transition, full band gap, and then the two sub-gap transitions. Now, the main assumption we're doing here is that holes that are found in this little well right here can escape by some mechanism, for example, thermal. So that's the main assumption here. Now, knowing that these levels here, the number of levels and their position, is controlled by essentially the dot size and indium content, well, my goal was then to calculate indium content and dot size and maximum efficiency. Or more specifically, to have these transitions here match those predicted by the detailed balance calculation. Now, before we move on to actual energy level calculations, let me tell you why we're actually interested in this material. It was used by Zipping-Lee's group in McGill to grow LEDs. So if there were successful at doing LEDs, it's only natural to think about using these as solar cells also. And here we have a few figures from one of their papers here. The first one to the left, we have photoluminescence plots from their various devices. And the second figure here shows a forest of gallium nitride nanowires. And the following two figures zoom in onto one of these little wires here, and we can see inside here and more clearly here, they contain multiple gallium nitride on dots stacked one on top of each other. And as we can see here, these dots are kind of like disc shapes with the edges rounded out, kind of like pancakes, if you will. So for simplicity, for analytical work and all such, I'm going to assume that these dots are of cylindrical shape. So just to simplify calculations. Now, I remind you that my goal is to have the transitions between the levels match those of the detailed balance calculation, so we can be able to calculate the energy levels. So in order to do so, I use an effective mass model, which basically consists of solving Schrodinger's equation, but using an effective mass here, those of the band. So this has to solve on both conduction and valence bands separately. And since we assume cylindrical dots, the potential takes on a finite cylindrical potential. Now, without going through all the math, here's an example of what you get for your eigen values, or your energies, for a given set of parameters. So the first thing I want to clarify is this dashed line here represents the bulk band edge that you would have for the corresponding Indium content. And the highlight here is that there is quite a gap between the bulk band edge and your actual fundamental level. So what you end up having is, for when you have systems with high confinement, this is one dot, there is a volume of effective band edge that you need to take into account. So this effect happens for both conduction and valence band. So it's important to take this into account. And just to show you what the wave functions look like, so here for the same set of parameters, the same energy levels, here's what you get for the fundamental level. So what I'm plotting here is the square amplitude of the wave function through a slice of the cylinder, the cylindrical well. So as you expect, it's quite localized, quite centralized, and just a big blob essentially. But as you go to higher energies, you start seeing degeneracies and higher nodes and so on. And just to give you a bit of a look at what they seem like. But the important thing for us is this fundamental level, because it is this level and the conduction and the valence band also that will give you your effective band gap. Now, the missing key here, which I haven't given you yet, is how we track from band gap or energy levels to Indium content. So the procedure we took basically was, well, we fixed the intermediate band optical transition to match that of the 1.9 predicted by my detailed balance calculation. And then, once you fix your dot's radius and height, considering a centimeter, you basically have a system that has this band gap. And through these results here that consists of theoretical EFD calculations from Van der Waals for bulk Indium gallium nitride, we can track for a given band gap what is the corresponding Indium content, or vice versa. So using this procedure, here are essentially my main results. So the way to read this graph is, let's say you want to grow a quantum dot that has a height of 3 nanometers, and let's say a radius of 5 nanometers, the corresponding Indium content would be 0.8 to have the maximum gauge, to have your transitions in the dot match those predicted by detailed balance calculations. And this can be done for multiple parameters and so on. So these curves gives you the right combination of dot height, radius, and content to maximize your efficiency. Now, for future work, we are working on a more sophisticated K.P model, which we really want to show today, but sadly it's not quite there. We also need to include strains in the devices, because strains in variables are very, very important. And it can be included through this model right here. And we need to investigate are the holes in the valence band in the quantum dot valence band actually staging or not. Because this is important, because if not, you may treat it like it's entirely And obviously we need to compare the measurements to verify theory. So my take-home message is basically the system's usual potential for 90% under full concentration is considerable. It's quite quickly to see. And we are able to predict some growth parameters. Now we just need to verify if they make sense, if they compare metric well to experiment. So thank you for your attention.
Thank you very much. Questions? Please. Okay.
Can you mention a bit more how you treated the faults in the system?
Oh, okay. Well, when you're solving the math model, I essentially take the math for the valence band for the whole. I'm basically meaning that both conduction and valence band the same way, just your energy levels are inverted as well. Oh, I use the heavy volt. Yes, heavy volt. InGaN nitride, the heavy volt, light volt, are the GaN point, and I use, if I remember correctly, I use the heavy volt.
Okay. Any questions? Okay.
Can you say a little more about your detailed balance calculations? And you mentioned that non-radiative transitions were not included. Were all possible radiative transitions included, like transitions from the
all radiative transitions are possible. And in the first case, the non-radiative combination of cases is most optimal to get out of this. You want more information on
trying to think, do any of the transition rates or anything that come into play?
No, because you take your calculations that your device is somewhat infinite. You just assume that all photons that can be transitions will eventually be. So all the photons that can be will be reflected.
Questions?
To follow up on my question, you say you use the heavy volts, why not the light volt?
To be honest, I don't quite remember. Hold on.
I have a question. You mentioned you can compare with experiments, right? Now, coming to the real life. So you have a nice model, but the dot with a huge amount of depth, communication center, and so how will you interplay with that?
And such will be hard to take into account. These structures are normally pretty don't have much interest in my knowledge, but at the surface, they do have a core delta